This conference will now be recorded.
Hello everyone. The topics that we are going to discuss today: nomenclature of elements with atomic numbers greater than 100, then periodic trains in different types of properties. And these properties, there are actually different properties, but today we'll try to cover atomic radius, ionic radius, ionization energy, and related problems. So when there are elements that are having very high atomic number means greater than 100. So it may happen sometime that when the elements they are newly discovered, probably right now they are having some particular name, but when they were actually discovered, then immediately it cannot get its actual name. Then there is some based on some rules we can give any name. Okay, so we will see that here, that how we can find this nomenclature based on some rules. Obviously it is for newly discovered elements. Fine. So this name is basically derived directly from the atomic number. So once you know the atomic number of this element, suppose 101, 120 like this. If we know this, then using these numerical roots, we can find the nomenclature. Fine. Now for the digits starting from 0, 1, 2, 3 up to 9, we will use some specific terms. So see, here we have the digits starting from 0 ending at 9, and the root words that we are using: nil, then un, then bi, tri, quad, in this way up to 9. And there is abbreviation also. Abbreviation is very simple. It is just the first letter. So for nil, the first letter is small n, then un, it is a small u, b, then t, q, p, h, s, o, and n. Fine. So this is the abbreviation. Now how we will use it? These numerical roots that you are seeing here, it is corresponding to the atomic number, and all this will be put together. And after putting them together, at the end, we have to add this suffix I, U, and M. Okay. Now, suppose I am considering these two digits, 1 and 4. So it will be un and then quad. Fine. And then another number, that also we have to choose, because there will be total 3 numbers. It is greater than 100, so minimum 3 numbers will be there. But you have to end it with IUM. Fine. Now, when you will do so, it may happen that the final letter, just for example, ENN, which is for the number 9. So ENN is there. And then after 9, suppose there is 0. So you have to use nil for that. Now n is ending with n, and then you are writing nil, there is another n. So what you have to do, you just have to omit one n, and it will be a nil. So it is not n nil, it is a nil. Similarly, when there is bi or tri, and after that you have to use this iam. So there is this I coming 2 times. So when same letters are coming 2 times, we are just omitting one of them, and it is now becoming triam. Here we have these 2 examples. One is having atomic number 101, another one is 111. So 101, it will be un, which is for 1. Then for 0, it is nil. And then there is another one for which you again you will write un. And as we know, we have to end it with the suffix which is IUM. So the recommended name will be unnil. Basically, the pronunciation is unnil, unnia. Okay, but symbol, you just have to choose the first letter. So the first letter is, it is U. Then for 0, it is nil. So this N we have to use, and then another un, so U. So you have to just choose these 3, U and U. So that is why now it is U and U, but that is a symbol. Remember, for normal names, for example, nitrogen. So the name is nitrogen, but when you write the symbol, you simply write capital N, right? So similarly here also we are using the symbol by taking the first letter of each of these terms. Now for 111, this un, it will come 3 times, so it will be un, and you have to end it with ium. But if you want to write the symbol, it will be u only, because there are 3 times we are having the number 1. Fine. The symbol of the new element is derived from the first letter of the numerical roots. So that we have already seen. So these are the numerical roots, that is un, bi, tri, quad, pent, hex. So we will take only the first letter of these numerical roots. Fine. Now we will see some examples. Starting from 101, and it is up to 118, because that is the maximum number of elements we have in the periodic table. So 101 and 111, these two we have already seen. Let's take another example. Suppose 108. So 108 means you have to take this un, then you have to take nil, and then you have to take oct. So that is why it is un, nil, oct, and then you have to end it with ium, which is common for any name. And what will be the symbol? The symbol will be u, which is coming from un, n, which is coming from nil, and o is coming from oct. But actual name of the element, because it is the name is already given, that is also mentioned, and the symbol. Another example, if we take, suppose 116. So 1 un, then again 1, another un, and then there will be hex, and that is for the number 6, and you have to end it with ium. Okay, so it is uuh. And if we want to take this particular example where bi or tri, suppose just take this one, 102. So it is un for 1, nil for 0, bi for 2. But after bi, which is for 2, and we have to end it with ium. So don't think it will be bi iam. No, it is not like this. This is not the correct way to write. It is actually bi iam, because one I will be removed. Okay, that is already mentioned in the previous slide, where how to write it, all the rules are given. Now based on this, if we solve this problem, the idea will be clear. The question is asking the atomic number of the element un, nil, nium, that is given. So un, we know it is 1, then nil, it is 0, then we have e double n, that is basically 9. So it is 109. So option D, that should be the correct option. Very easy. And what will be the symbol? Symbol will be U, then N, and then E. U and E. Next problem, the IUPAC symbol for the element with atomic number 118. Now the number is given, you have to write the symbol, not name. Now 119, that means U, it is un, then again un, and for 9 we know it is sorry, ENN. It should be U, then U, and then E. So UUE, that is present in this option. So atomic number 119, N, and it should be ending with IM. Though it is true that the full name they are not asking, they are asking only the symbol. The symbol is fine, UUU. But if suppose the name is asked, in that case it will be N, E double N, and then you have to write IUM. That is a suffix. So after finishing this, next, periodic trend in the properties. Periodic trend exists because of similar electronic configuration of the elements. Now, similar electronic configuration, when I'm saying, that is possible in a respective group, right? And when you are moving in the along the period, there is change, that is one extra electron is added subsequently. So there is also change in electronic configuration. So similar electronic configuration, that is only for groups, not period. Fine, because in period gradually, that is a common pattern is not maintained, but when you are moving down the group, the common pattern is maintained. Suppose if you just take example of group 2, common pattern is ns2. So any element you choose, it will be either 2s2 or 3s2 or 4s2. So this is a common pattern, that is ns2. Now, what are the properties for which we are doing this discussion? These properties are, here it is mentioned, electronegativity, ionization energy, electron affinity, atomic radius. There is also another radius which is ionic radius that we will discuss today, and then melting point, metallic property, non-metallic property, etc. Now, why it is important? Because if you know the trend, it helps chemists to quickly predict an element's properties. So, for example, again I am taking, suppose, group 2. Now, group 2, there are different elements, fine, that is Be, Mg, then Ca. Now, the first element, beryllium. Now, as we are moving down, what will be the change in a particular property? Just take example of atomic radius. So when it is we are moving down, suppose it is increase or decrease, whatever it is, you know that property. So if the first element, its atomic size is given, obviously you can now have the idea what should be the atomic radius of the other higher members of the same group, because you know that down the group atomic size increases. If you know this fact, and if the value of Be, that is the beryllium, its atomic size is given to you, you can easily predict that down the group for the higher member, as you are moving to Mg, to Ca, to strontium, obviously it will increase. So in this way, it will help us to quickly predict. Similarly, if you are moving in a particular period, suppose beryllium, it is from second period, and now you are moving in the second period from left hand side to right hand side. In this case, atomic size actually decreases. So if you know this trend, you will be able to predict that for the next element along the period from left to right, what should be the atomic size. You can have some idea. So in this way, periodic trend helps us to predict the element's properties. Okay. Here we have very a picture, though from this picture right now details you will not be able to understand, but in a nutshell, if we consider what are the trends of these different types of properties, obviously there are some exception because of some special cases that we'll discuss separately when we will individually focus on these properties. Okay, so here you can see we have taken electronegativity, atomic radius. So from the arrow you can understand when you are moving down, basically size increases, and when you are considering from left hand side to right hand side movement, that is period, then atomic radius increases towards left hand side. That means when you are moving from left to right, it is decreasing. But again I am saying, remember one fact, it is a more or less general trend, but always there is exception. Okay. Similarly, ionization enthalpy, it is increasing as we are moving from left to right. But ionization energy or enthalpy, when you are moving down, that will actually decrease because the arrow sign, that is upward. Upward means it is increasing towards that direction. So here the arrow sign, it means to that direction where it is increasing, because directly it is not mentioned why it is increasing or decreasing. But when it is upward direction, that means it is increasing. When it is downward direction, that means increases towards down. Fine. Now the first property that we'll take is atomic size. So first we'll see what is the definition of atomic radius. Atomic radius is 1/2 the distance between the nuclei of two atoms. Now two atoms must be present. Suppose if I am writing like this, one atom then another atom. This is the nucleus, this is the nucleus. Now if you join these two nucleus, now take the half of it. And if you are considering, suppose imagine only one atom is present as you are seeing in this picture, then you just have to take this distance. Okay, but when there is another atom, obviously another same atom, then obviously another r is there. So now if you join these two center, the distance is 2r, so you have to take half of it. But if you consider individual atom, then it is simply r. But why we do not consider individual atom? Why the definition is given considering two atoms? Why it is not based on one atom? This is because it is not possible to measure the radius of an isolated atom directly. Though here the picture is given like this, but actually, you know, electron, its position is not fixed. There is a probability. There is an electron cloud surrounding the atom. So what is actual ending point? Though here defined line is given, but this is actually imaginary. Here, though from the picture it seems it is defined sphere, but actually if you consider isolated single atom, where the electron cloud is actually ending, it is difficult to get that. So that is why if you want to measure radius of an isolated atom, it is not possible. There is a no sharp boundary. Though from picture it seems boundary, but actually there is no sharp boundary. So that is the reason the definition is given in such a way as if two atoms are present side by side, and then you are connecting the two nuclei, and then you are taking the half of that distance. So an estimate of atomic size can be made by knowing the distance between the atoms in the combined state. Once you know this, you just have to take half of it. If the molecule is non-metal, suppose chlorine, then it is half of the distance between two atoms as the definition is given in the first statement. Okay. So for non-metals, it is half the distance between two atoms when they are bound together by a single bond in a covalent molecule. So it has to be covalent molecule, it has to be single bond, then the definition is applicable. But okay, you can see now we have taken two atoms and you are joining these two nuclei. The distance is d, but r is basically half of d. Fine. So it is 1/2 that is covalent radius or atomic radius. Atomic radius basically you can say more general term, because when I'm saying covalent radius, obviously the molecule is there is covalent bond, but atomic radius it is more general. Okay, so when I'm talking about covalent radius, it is 1/2 of the internuclear distance between two identical atoms that are linked together by a single covalent bond. So it has to be covalent bond. Fine. And just simple idea I will give you what is covalent bond, though details are basically present in another unit which is chemical bonding. But if we that is if I'm giving a very simple primary idea what is covalent, then it is basically, suppose there are two atoms A, or it may be A or B, and there is a single bond between them. So this single bond is basically containing two electrons. One electron is given by left hand side atom, another electron is given by right hand side atom, and then these two electrons are shared equally by them. Okay, so proper sharing, equally sharing, this is actually covalent bond. And if I'm talking about ionic bond, then one atom is completely giving electron, another atom is completely accepting electron. So suppose one is A plus, because it has completely given electron, another atom accepted that electron, then it will be negatively charged. Now see, it is not equal sharing, because in the previous case one electron given by left hand side atom, another electron given by right hand side atom. But now the thing picture is different. Now one has completely given, another one is completely accepting. And that is the reason there is generation of positive charge and negative charge, and there will be some electrostatic interaction between these two, and that is actually ionic bond. Fine. But when I'm talking about covalent radius, you have to consider this type of covalent bond, not ionic bond. So this is a definition of covalent radius, but this is for non-metals. But if there is metal, suppose both the atoms are metals, now it is different. Now what you will do, it is half of the internuclear distance separating the metal core in the metallic crystal. So for metals, they exist in crystals and there are some metal core. Okay. Now in between these two metal core, what is the internuclear distance? You just have to take half of that distance. Fine. And it can be measured by X-ray or other spectroscopic method. But right now we are just focusing on covalent radius. So for metallic radius also here definition is given. But before that, if you look at the left hand side picture, this is the covalent bond between two chlorine, because you know chlorine is diatomic, Cl2. So this experimental internuclear distance is given. Suppose this distance is d, 1.98 angstrom. Covalent radius of chlorine will be half of this distance. So d of chlorine, that value is given, which is 1.98. But individually, if you consider, it is 2 of RCl, that is covalent radius. So that is why you just simply have to divide it by 2. You will get the value 0.99 angstrom. What about metallic radius? It is defined as 1/2 of the distance between two adjacent metal atoms in closely packed metallic crystal lattice. For example, just you have seen covalent radius example with chlorine molecule. In this case, we will obviously take a metal. So we have taken copper atoms. It's crystal lattice. The distance between the adjacent copper atoms in the solid copper, the distance is 2.56 angstrom. So obviously, the metallic radius will be half of this distance, 2.56, because according to the definition, it is half of this. Now, metallic radius, it can be calculated also using the unit cell length of metallic crystal, and that is actually the ideal way to measure it. But details, that is not part of this unit, that you will find in the solid state unit. But more or less, if we want to give some initial idea, you can say from this definition that it is 1/2 of the distance between two adjacent metal atoms. Fine. Now, if this is atomic radius definition, now we know. Next, we will see how this radius, or you can say size, it is changing along the period and also down the group. So first we will see what is the variation in period. Atomic size generally decreases as you are moving from left to right. But remember what is mentioned here, generally. So it is not always universal. There may be sometimes some exception. Sorry, but generally it is decreased as you are moving from left hand side to right hand side. And if you consider group, then it is opposite. There is increase down the group. So this is the initial conclusion we can draw. But how we are reaching this conclusion, what is the reason behind it? Now we will see that. When you are moving from left hand side to right hand side along a period, we know that valence electrons are gradually adding to the same shape. Just for example, if you take carbon, which is from second period, and the next element is nitrogen. So for carbon, outer shell electronic configuration is 2s2 2p2. Let me write it clearly. Suppose we have carbon, which is 2s2 2p2, and just the next element nitrogen, and in this case one more electron added, so now it is 2s2 2p3, and the atomic number of carbon is 6. Atomic number of nitrogen is 7. So when you are moving from left to right, there is extra valence electrons are adding. Similarly, if you move to the next element after nitrogen, atomic number 8, oxygen. Now the configuration is 2s2 2p4, then 2s2 2p5. In this way it will move on. So what is happening here? First of all, valence electrons are added. And another thing is there, at the same time, protons are also being added to the nucleus. So valence electron added, that is fine. That is change in the outer shell electronic configuration. But just imagine about the nucleus. In nucleus also, as atomic number is increasing, there is increase in proton number. So for carbon, there are 6 proton. For nitrogen, there are 7 proton. Next element, oxygen, 8 proton. So positive charge in the nucleus is also increased. So making it more and more positively charged. I'm talking about the nucleus. So these two things are happening when you are moving along the period. Now, these two effects, the effect of increasing proton number, this effect, that is this effect, it is greater than that of the increasing electron number. Now, one effect is predominating over the other, and as a result, there is greater nuclear attraction. So, it is true that when, suppose this is the nucleus, I'm just drawing one orbital, and there is electron. So, there is some attraction. Now, you are adding another electron. There will be some repulsion also. Now, because of this repulsion, you can expect that there should be some increase because they will try to move apart from each other. But it is also true, as you are moving from left to right, this positive charge is also increasing. Okay, so the attraction between the nucleus and the outermost electron, that will also increase. So these two effects, they are actually having some opposite effect on the variation of size along the period. If you consider only increase in number of valence electron, it seems as if size should increase. But if you consider this nuclear attraction, then because of this increased attraction, the outermost electrons, it will be shrink, size will decrease. Now this second factor, both are having opposite consequences. But the second factor, that is increase in number of proton, that will predominate. That is mentioned here, that the effect of increasing proton number, that effect is more important. So what is the overall net effect? The net effect is atomic size decreases from left hand side to right hand side. That is mentioned in the first point. And the valence electrons, now they are held closer towards the nucleus of the atom. So this is the reason and for the variation in period, that is decrease as you move from left to right. But why in group it is increasing? Now we have to know that. When you are moving down a group, we know principal quantum number increased. Suppose you are moving from lithium to sodium. Now lithium is from second period, sodium is from third period, but they are in the same group. Then there is potassium. So here principal quantum number involved for lithium is 2, for sodium it is 3, for potassium it is 4. So it is 2s1, then 3s1, then 4s1. I'm talking about the outermost electronic configuration. So because of this increase in principal quantum number, that means new shells are added, and Why added? Because they will accommodate these newly added valence electrons. So when new shells are added, obviously now they are further away from the nucleus. Okay. So that is the reason when you are moving down, because of these extra added shells, there will be increase in size. Now you can also say that when you are moving down, atomic number is obviously increasing, right? Now for lithium it is 3, for sodium it is 11. Now when atomic number is increasing, proton number is also increasing. And when proton number is increasing, there should be greater nuclear attraction, just as you have seen in the previous case. I'm talking about the variation in period. There we have seen that the nuclear attraction factor is overcoming the other factor. Then what we should consider here? It is true down the group new shells are added, but down the group nuclear attraction is also increasing. If you consider nuclear attraction factor, down the group size should decrease. And if you consider new shells are added, then down the group size should increase. So opposite consequence. But which factor predominates? This factor predominates. So it is true that there is also increase in positive nuclear charge with increase in atomic number down a group. So for lithium to sodium, it is changing from 3 to 11. So in this way, there is increase in positive nuclear charge. But the effect of greater number of principal energy shell, that is extra added shells, that factor outweighs the increase in nuclear charge. Outweighs means it is overcoming the other factor. So ultimately, which factor is winning? The factor that new shells are added, that factor is winning. And the net effect is when you are moving down the group, there is increase in size. Fine. Here we have taken period 3. Period 3 starts with sodium, that is group 1, then group 2, 3, 4, up to, it is after, sorry, it is not 3, it is 13, because we have not considered the D block. Now why we do not consider D block? Because in case of D block, there is, the discussion is done separately. When we talk about periodic trend, you will see mostly we consider the main group elements. Main group elements means in last class we have discussed about it. What is main group? It is S block, these two, and it is P block. We normally do not consider the D block, because in D block, because of some special property related to d orbital, there is very slight change or very little variation in their size, and it is generally discussed separately for D block. So when you actually consider the general trend in the periodic table, we normally do not consider d orbital. Okay. So here we have this first group, second group, then group number 13, then 14, and up to 18. So you can see there is smooth decrease as you are moving from sodium to Mg up to argon. And then we have taken another example which is based on variation in group. Which group we have taken? Look at these elements. They are from group 2. So for group 2, as you are moving from, this is second period, this is third period, fourth, and in this way it is 5 and 6. So now period number is changing, but group is fixed, that is second group, and you can see there is increase in size. Fine. Now the whole periodic table, if we consider, now you can see the D elements also, but for D elements the size variation is very insignificant, as if it is almost same. That is very little variation. It is not same, there is little variation. Fine. So if you consider these S block elements, you can see down the group, and it is very easily we can observe this. There is increase when you are moving. You can also consider any group in the P block. Suppose you are moving down from gallium to indium, there is increase. And when you are moving from left to right, there is decrease. Fine. For F block also, again I'm saying that when we discuss periodicity, it is mainly main group elements. Normally under normal condition, D block, A block, these two are not considered, okay, because their chemistry is highly influenced by the F orbital and D orbital, and that is why there is a separate unit for them where it is discussed separately. But this is overall picture. You can see how the size is changing along the period and also down the group. The atomic numbers are also given for your convenience. After talking about atomic radius, what is ionic radius? Now, atomic radius, obviously it is radius of atom, but when I'm talking about ion, it is no longer neutral, right? So ion means, just take sodium. It is neutral atom. But if it has lost one electron, it will become sodium plus. Now it is not sodium atom, it is sodium plus cation. Similarly, if you take Cl, it is atom. But if you add one extra electron, then it will become chlorine anion. Now one question may arise in your mind. Why I am not considering Cl plus or Na minus? Because that doesn't happen. Na, as it is metallic in nature, it will always lose electron, and after losing electron it will reach the noble gas configuration of neon, which is a stabilizing factor. So that is why Na minus is not possible. Sodium, it is metal, it cannot be negatively charged. Similarly, Cl, when it accepts electron, it achieves the next electron noble gas configuration, so it will always accept electron, it will never lose electron. Okay, that is the most common thing. So that is why I have considered anion with this non-metal chlorine, and I have taken an example of cation which is generated from the metal sodium. Now how we will define atomic radius? It is defined as the distance from the center of the nucleus of the ion up to which it exerts its influence on the electron cloud of the ion. So for ion also, for atom also, you know, there is electron cloud. In this case, whether it is positively charged or negatively charged, then also it is, the definition is like this: distance from the center of the nucleus of the ion. Suppose Na plus. Consider the nucleus of Na plus, nucleus of the ion up to which it exerts its influence of electron cloud. So the influence of Na electron cloud of Na plus, it will be up to a particular point. So this distance is actually ionic radius. Now, trend of atomic size that we have seen, it is almost same when you consider the trend of ionic radii. But you have to remember that neutral atom, when we have considered, that is one situation, and when you are considering ion, now ion is you cannot form any ion for any element. There is some specific rules for that. For example, you cannot have Cl plus or any positive charge over non-metal, or you cannot have sodium 2 plus. It is not possible. Okay, because if it is 2 plus, you have removed one more electron from sodium plus. That means you are basically breaking the stable configuration of neon, which is highly energy requiring process. So that is why sodium 2 plus is not possible. But 2 plus charge, sodium 2 plus not possible, but 2 plus charge, that is very common if you consider any element from group 2. For example, Be 2 plus or Mg 2 plus. But just before Mg 2 plus, there is sodium plus. Now, for atom, suppose Na and next element Mg, you can easily compare that from sodium to Mg, you are moving left to right, so it will decrease. But now, as there is some positive charge, and it is not same positive charge, it is +1 for group 1, it is +2 for group 2. So they are not having same type of charge. So how you can compare? So that is why finding atomic size variation, it is comparatively more common, or you can say more popular in the periodic table. But finding the periodic trend for ions, it is comparatively not so popular. but you can do so in a particular group, because when you are considering a particular group, all of them will form same type of cation. That is, if you consider group 2, it is always 2 plus. If you consider group 1, it is always potassium plus, sodium plus, lithium plus. So when same type of ion is there, you can compare. But for different types of ion, comparison is difficult. Okay. So that is the reason, as each atom is unique in its ability to lose or gain electron. It is not that any atom can gain any number of electron or any number of electron they can accept. No, it is not like that. It is their unique property. So that is why you cannot compare directly. So this is the reason periodic trinity ionic radii, they are not as ubiquitous, not so popular. Okay. That is, just in any group or any period, you cannot find that trait. It is possible only in some cases. As trend in atomic radii across the periodic table, that is, if you compare with that, it is not so ubiquitous. And trends must be isolated to specific group. If you consider a specific group, then trend is fine, especially this S block. And if it is considered for either cations or anions, that is, you can compare with the cations, but suppose you are comparing beryllium 2 plus with Cl minus, it is absurd, it is not possible. Fine. So remember, it is not so popular as you see in case of variation of atomic size. But this picture will help you to have some idea. Here we have taken some cation. This is group 1, this is group 2. Okay, it is mentioned here, and it is group 13. So the red part, that is actually the cation, and this gray part, that is actually the atom, neutral atom. And the gray part value is given 134 picometer, and the red part, which is the size of the cation lithium plus, that is 90. So obviously when you have removed the electron, the size will always decrease. It has to be. So that is why from all the left hand side red colored value, which is the value of the cation, and the gray part, which is larger in size, because now it is neutral. So the neutral values are given in black color. So when a neutral atom gains or loses an electron, so when it gains it is anion, when it loses it is cation, then atom's radius increases or decreases respectively. So when it is forming an anion, it is increased in size. When it is losing electron and forming cation, obviously there is removal of electron, size will decrease. So that is the reason you can see for all these cations compared to neutral atom size, the value is less. Now that is all about mostly metals. What about non-metals when they will gain electron? Here we have group 16 and 17. So here this blue part, that is actually the size after acceptance of electron, that is the size of anion, and the gray part, that is the original neutral atom. So obviously you can see, just take Br. When it is neutral bromine atom, it is 114 picometer. When it has accepted electron, now the size is highly different, right? For oxygen 73, when it is neutral, but when it has accepted 2 electron, now the size is large, 126 picometer. Now when if you directly consider F minus, Cl minus, Br minus, I minus, now you can compare, because all are formed, all of them have formed similar type of anode. Now you can compare. But directly, suppose you are comparing Rb plus with F minus. No, it is not possible. They are not in common ground. How you can compare? Fine. Another thing we have to know for ionic, when we are discussing ionic size, is isoelectronic species. You can get question regarding this. So isoelectronic species, from the name you can understand, the species will have same number of electrons. When I'm saying species, I'm meaning some cation or anion. It may be cation, it may be anion, or it may be neutral atom, any species. So for the atoms or ions that are containing same number of electrons will be called isoelectronic species. Now as they are having same number of electrons, obviously you can expect them to have same degree of electron-electron repulsion and also shielding. Here we have taken some element, not element, we have taken basically ions. So first we have taken oxygen, its atomic number is 8. Okay. Atomic number is 8. For fluorine, it is 9. For neon, it is 10. I'm talking about the neutral atom. Atomic number is Z value. For Na, 11. For Mg, it is 12. Now, when Mg has lost 2 electron, it is basically now 10. When sodium has lost 1 electron, it is 10. Neon, it is neutral because noble gas, they will not lose or gain electron. If when accepted 1 electron, it is F minus. Now it is 10. When oxygen accepted 2 electron, it is also 10. So now all of them are having same number of electron, and the common electronic configuration, which is basically the configuration of neon, it is now true for all of them. So oxygen normal configuration is 1:2, 2:2, 2p4, 8 electron. But now 2 electrons are extra. So now it is 2p6. Similarly, Na plus, suppose Mg, what is electronic configuration? It is 1:2, 2:2, 2p6, 3s2, but 2 electrons less. So it is now up to 2p6. So basically, all of them are having same electronic configuration. So that is why they are isoelectronic species. Though they are having same number of electrons, but remember, they are not having same number of Z. That is, Z is still 8, 9, 10, 11, 12. That is, atomic number is still same. Electron number is changed. So they have differing number of protons still, and that is the reason their nuclear attraction is also different. Now their radii would be different because of their different nuclear charges. And remember, when it is isoelectronic species, that is all are having same number of electron. For this type of species, suppose you have 5 to 6 species, you can easily compare their ionic sizes. Though here directly the picture is given, you can easily understand oxygen is having maximum size. Then F, then neon, then Na plus, and at minimum position there is Mg. So this sphere sign is there. Now why it is so? Because under the same condition, when they are having same number of electron, now because of this nuclear charge, as maximum nuclear charge you can expect for Mg2 plus. So obviously its size will be minimum. Similarly, vice versa, oxygen, Z value is minimum here. So that is why its size will be maximum. Okay, so in this way you can find their order, that is ionic radius order. Now based on this atomic size, if we solve this problem, the correct order of atomic radii, here 4 elements are given: carbon, cesium, aluminium and sulfur. So what will be the correct rate? Now it is not ion, it is related to atomic radii only. Now carbon is from which group? It is 14, so it is in P block. And cesium, it is from S block. Aluminium again P block. Sulfur, that is also from P block. So now you have to imagine the periodic table, and you have to combine 2 factors. One factor is down the group, there is increase in size, but when it is moving along the period, there is decrease in size. So keeping these 2 points in mind, you have to draw the net conclusion. That is what will be the ultimate order. So here we have this S block and P block, only main group elements. So cesium is here, right? Now cesium is here, carbon, and we have aluminium, and we have sulfur. Now you can easily compare aluminium and sulfur because aluminium will be having higher size. They are in the same period. Aluminium is before sulfur, so it will be having higher size compared to sulfur. But that is present in all the options. So it will not help you much. Now see, cesium it is at which period? It is second, 3, 4, 5, 6. So it is in the highest period. So obviously its size will be, it should be maximum. Now maximum size for cesium, based on that fact, you can choose only option B and C, right? And in both, so any of these two will be correct. You can cancel these two. Now if these two are correct, after cesium in both options there is aluminium. But after aluminium, is it carbon or is it sulfur? So see, carbon and sulfur, if you compare, that is group wise, there should be increase in size, right? But if you consider, that is, it is as if diagonal type position. That is, if you move right, if you only consider this factor that along the period there is decrease. But remember, sulfur it is not in the same period, right? So it is not in same period, but it is in the next group. So next group means obviously size will be high. But it is also true the next group, if it is directly below carbon, you can confirm, you can be confirmed that yes, it is high. But it is not just in the next group period, but also to the next position. But still, when you are moving from second to third period, this extra added new shell, this factor will predominate. So that is the reason now sulfur will be higher in size. Fine. So sulfur will come after aluminium. As we move from L to R, left to right, atomic size decreases, and when you move top to bottom, atomic size decreases. And combining these two, this should be the correct option. Fine. This is very simple, and this is related to ionic radius. Ionic radius of Na plus ion is given, which is 1.02 in angstrom unit. Now it is asking, what about Mg2 plus and Al3 plus? Now it is true that they are not in the same group, but still you can compare. How? Because when it is sodium plus, it is basically 10 electron. When it is Mg2 plus, again it is 10 electron. When it is aluminium 3 plus, this is also 10 electron. Remember, they are actually isoelectronic species. Aluminium atomic number 13, but 3 electron removed, so it is also 10. Now when they are having same number of electron, you just have to consider the charge. Maximum charge means size is less, so the order should be maximum size for Na plus, after that Mg2 plus, then it is Al3 plus. If you keep that point in mind, the value for Mg2 plus, that will come first, then Al3 plus, because there is respectively. So it must be lesser than 1.02. So this cannot be correct. Now this may be correct. This may be also correct. This is also correct. But which one is actually correct? Here C is not possible, because in case of C 0.85 but 0.99 for aluminium, but aluminium should be lesser than this. So that is why this should be the correct option. 0.72, that is for Mg, and this is for aluminium. This cannot be true because the next value is higher. This is also not possible. 0.72 is greater than 0.68. So option B should be the correct option. More discussion we will also do in the next class. Today we are ending here. Thank you for listening.